Okay, welcome. Today we are going to talk about something totally different is a strong word, but something entirely different than what we have been studying recently. And our topic for today is the problem of, let me write it down, region segmentation. And I will put the region into parentheses because segmentation is a more general term for the following problem. So the problem we are going to study is we want to, given an image, we want to segment it into coherent parts. If we look around in the world that surrounds us, we can make out objects. For instance, we can recognize all these chairs, and the table, and maybe the wall or the whiteboard. We perceive them as individual objects. And one of the reasons for our brain being able to perceive physical objects like this as okay, now, one of the reasons why our brain can perceive these objects that surround us in terms of homogeneous physical units is that they, of course, have characteristics which distinguish them from their surrounding. They are, from the point of view of looking at these objects, such as the whiteboard, homogeneous. They have a characteristic which we recognize for certain parts of the scene and which is different in other parts of the scene. That is, these visual characteristics of these objects allow us to segment a scene, or an image in our case, into different parts. We are looking at the problem of how to do that automatically. So we want to segment an image into topologically connected regions. So I talked about coherent parts, and of course, if we take a picture of the world that surrounds us, we can understand these coherent parts of an image as well, regions in an image. And a region in an image is a part of an image where the visual characteristics of the image in that part have something in common. Our problem is to look at how we can do this. And this is again something, a picture or two pictures in this case say 1,000 words. So here are examples for the problem setting. Say we are given an image and there is a certain region within this image. Let me, single it out. So it has a different color than all the other pixels in this image. So the pixels in this region have a different color. This is what makes it a region. There is something different for the pixels within this part of the image than for the other pixels. And here is another example. I don't know. Need another rectangle inside this thing. And this time, I don't know, I will indicate the characteristics, the different parts of the image like this. So, these are the two images we are given to explain the problem of region segmentation. Well, in both cases, this quadratic or rectangular area in somewhat the center of these two images sticks out because, again, pixels inside these areas have different characteristics, color characteristics, than the pixels surrounding it. This here, however, is something where we would say from the point of view of doing it automatically is very easy. Because here, this really has to be understood in terms of, say, something black on top of something white. This here is my attempt to show something textured. So the different stripes here are not to be understood as different colors, but indeed as, you know, stripes. So there's vertical stripes and horizontal stripes. And we would say that there are two kinds of texture in this image. And texture can, of course, be something arbitrarily complex. Here I have chosen two rather simple textures. But let me say this is difficult. Now, why is this difficult? To come up with an algorithm that would automatically say there are two characteristically different components in this image here. If these pixels are all white and these are all black, we just look at the pixel values. If these are white pixels and these are black pixels, then, well, this is a white pixel and this is a white pixel. We would not be able to sort of realize that these two white pixels have a different characteristics. So we would, for instance, try to look at certain local areas of the image, tiny image patches, and we might actually count the number of white pixels in such a patch and the number of black pixels in such a patch. In this cleverly chosen example, that wouldn't help us, because there's a white, black pixel, and here there's white, black. So, like, simple counts like that do not reveal that visually this area has a different characteristic than this area. So situations like these are easy to handle automatically. The reason is that these are regions of distinct but rather homogeneous color. So segmenting color images is not that difficult. These here are regions of distinct homogeneous texture. Right? And a texture is something else than a color. A texture is something that involves a spatial characteristic, some sort of a spatial statistics. And that's again, like if we were to resort to very simple statistics, such as just count the number of colors that occur in a small patch of an image, we still would not be able to distinguish these two parts of these images. And therefore, this is the problem of segmenting images into well topologically connected regions. That is to say, let me introduce another region here, like so. This image now would contain three regions. The background region, this one, and we would understand them as three regions because even though this region and this region have the same texture characteristic, they are not topologically connected. They don't touch. There is something in between those two regions. And so therefore, we would understand this as a situation where there are three different regions in the image, so topologically connected regions. From a very abstract point of view, I just want to point it out. This is from sort of the machine learning and pattern recognition point of view. What we are dealing with is a clustering problem. This is a clustering problem. I'm just saying that we will actually not explicitly treat it as such today. We'll again follow the rather pragmatic approaches in image analysis. All right, let me add something more before we look at how this can be done. So, given the examples I have just erased, we can understand what I am referring to when I provide you with the following assumption. And in order to be able to do something like this, to solve this problem of region segmentation, we need to come up with certain assumptions, because by and large the world is way too complex for us to expect that this can be solved in general, in its most general sense. The examples I've shown you here are really rather trivial again. Right? If we look outside, we can clearly see foliage and stems of trees and the sky. And how many regions are there if we look outside? It cannot be answered. This is if we were to take a picture of the trees outside and then hand it to, I don't know, 10 or so subjects and ask them to manually indicate the regions in that image, we would get 10 different results from 10 different subjects. This is, in a sense, a very ill-posed problem. It's actually very amazing that our brains can do it, but it involves a tremendous amount of uncertainty, which we cannot really expect to handle in general. So therefore, let's look at an assumption. So we assume that before we set out to devise algorithms or actually implement algorithms for this purpose, we assume that regions are homogeneous areas. Homogeneous areas. Well, that does not really say a lot, but we can try to make it slightly more precise. So that is to say that there exists a predicate, let me call it P, that holds for a region but ceases to hold if a region is extended, if the region is extended by neighboring pixels. Yeah, I guess I should give you another example of what I mean by that. So, how do I do this? Best thing is I do it in color. Here is an image, and is anybody red-green blind? If not, then I can use red and green. Here is a region within this image, and here is another region. And this abstract notion of a predicate could be that we would say pixel is red. Right? And if we apply this or evaluate this predicate somewhere in these regions of the image, it would evaluate to false. In this area of the image, the question is the pixel red would evaluate to true, and here it would evaluate to false. So therefore we could be tempted to summarize all connected sets of pixels for which this predicate evaluates to true into a region. Right? If we then extend the region by some neighboring pixels, it would not be a region anymore in that sense, because it now would contain pixels for which this predicate does no longer hold. This is what we're trying to do here. Okay, let me provide you with some more rigorous prerequisites here before we actually look into predicates. So when we set out to do this, then we implicitly assume the following to be given, to hold, so that we can do this in a reasonable manner. It's like we have the following formal prerequisites. First of all, we would hope that the overall image is indeed segmentable. That is to say that it can be understood as a union of homogeneous regions. I have deliberately not indicated the number of these regions, but let us assume the image will consist of possibly very many connected, topologically connected sets of pixels which share certain predicates. Second of all, we would hope, or ideally require, that two regions are disjoint. That is, that their intersection is empty if I is not equal to j. So, looking at two regions in the image, one is called Ri and the other Rj. And if we then were to look for the intersection, it should be empty if I and j are not the same. The third one is this idea that Ri is topologically connected. I already explained that by means of an example, so you don't have to re-explain it here. And there are two more. Yeah, I'll erase them. It's a shame. Oh, no. I'll have an insert here. Two more requirements. The fourth one is that there is a predicate that evaluates to true for all pixels inside such a region. Maybe, no, I don't do it. And the last one is that if we evaluate this predicate for the union of two regions, which we have identified as regions, it then should give false again if I is not equal to j. And this is all of what I have said here is to be recognized in this picture. Let me make this picture correct again. So I have to erase this. And color it in green. The whole image is a union of, in this simple example, three regions. Something we might be calling the background. Then we have a red rectangular square here and a green square. There is a couple of predicates for each of these regions. For instance, in the background we would say the pixels are white. Here the predicate would be pixels are red, and here it would be pixels are green. The regions we have segmented thusly are definitely disjoint. They are connected. Let me introduce another red region here, or make it green. And we would count this and these as two different regions because they do not touch. So all the regions in this example are topologically connected. If we were to compound two of these regions into a larger one, for instance this one, then the corresponding predicates would no longer evaluate to true. So we can, if we want to, formalize this problem of region segmentation to a certain extent and turn it into something which we can deal with algorithmically. And now it's time to talk about these predicates here. Right? This seems to be the most crucial thing here, because actually the algorithm for segmentation is already, in a very rough sense, is already here. Right? This tells us how to segment an image. We just have to have a predicate and evaluate it for all the pixels, and if it evaluates to true for two neighboring pixels, then it would include these two neighboring pixels into a region. What are these predicates? What are these predicates? Now, I have been using this term predicate, right? And the example I have given you so far was actually a very simple predicate. Example, so a predicate for a region could be the following. I don't know, let's say it evaluates to true if the distance between two pixels, and it's not the spatial distance, KL, so say the norm between the intensity values of two pixels, one at location ij and one at location KL, is less than some delta for all, how do I write this here, IL pairs IL and IJ. Difficulties reading my own handwriting. IJ and KL in this region. This is basically, it is not so much a statement about a specific color, but about color or intensity similarity. Right? If the pixels in a if the intensity difference between two image pixels is in a certain range, we would, for instance, be able to use that as a predicate. And it is false otherwise. Of course, given the examples we discussed earlier, can already recognize that this is something we can easily understand, something where we understand what the motivation behind this formulation is. But of course, it is something that is overly simplistic, something we may not expect to be of use when it comes to textured images. And therefore, I will now change the terminology and sort of get rid of the notion of a predicate, but we'll talk about features again. And this time we will be interested in texture features. Texture features. And we have talked about features before, right? And in particular when we discussed the SIFT approach, and if we ignore the fact that we have to compute key points, their location, scale, and orientation first, once we had them, we computed a vector of 128 dimensions for every key point and used that vector to describe what is going on in the vicinity of that key point. And I said these vectors are features. These vectors are local features of what is going on in an image. And features are, or the term features once again is just a way of expressing this idea where there is something characteristic, something that holds for this area of what we see but not for this area. And trying to formalize or write down what it is that distinguishes this area from what you see from this area you see is the problem of finding features. And so with respect to segmenting images that are highly textured, such as the scenery outside, we would need texture features. They are required to define these predicates, to define P. But in a sense, this predicate is actually the feature, right? Because the way I have talked about these predicates so far is that does it hold? Is it true that this pixel meets the following or has the following predicate? So this is actually to say, does this pixel have a certain feature? And in that sense, it's actually synonymous. And there are, of course, numerous methods out there. Numerous methods available. Let me ever so briefly just mention a few. So we could think of, for instance, intensity histograms. Intensity histograms. For a given pixel in an image, we again look at a neighborhood of that pixel. We somehow define the size of the, let's say 16 by 16 as in the SIFT case. And in that neighborhood of the pixel, we count all the intensity values. And again, I'm just referring to intensity images here for the sake of simplicity. Count the intensity values and bin them in a histogram. And the histogram, we would say, it will be a different histogram for most of the pixels in the image. So therefore, that histogram is a feature of that pixel. Right? We may, of course, compute, let me call it dense SIFT. Dense SIFT. The approach towards computing SIFT features we have studied recently. I mean, we can compute these features not just at key points, right? Who is there to prevent us from computing these 128 dimensional vectors at every pixel of an image? Nobody. But people have done it, right? And used these dense SIFT features, which are dense in the sense that they are not just computed at certain key points, but everywhere, as methods or ways to describe certain local characteristics. Another popular approach is called histograms of oriented gradients, HOG, which is just, I shouldn't say that, you know, loosely, but it is a certain variant of the SIFT features we studied. Very popular though can be computed very quickly, slightly simpler than stiff features, and so on and so forth. There's like, really there is numerous methods out there we could use in order to characterize what is going on in the neighborhood of a pixel. But the common theme to all the ones I have listed there is, and I have said it a couple of times, to consider local pixel neighborhoods. That is what they all have in common, that the feature is not computed from a single intensity value only, but from a collection of intensity values in the neighborhood of a pixel. And what we are going to look at in slightly more details right now is the idea of another kind of local intensity feature. We will now look at gray value, it's called gray value co-occurrence matrices, and I will call them matrix G. This is a feature that has a long history. I mean, I don't know, at least 30 years, so it's way older than this idea of SIFT features or Hawk features. This goes back at least 30 years, and the idea is based on an assumption. The assumption here is that texture, this is what we are after. We want to be able to characterize homogeneous textures, is characterized by the frequency of co-occurrences of pixels. It will become clear in a second. Pixels of common color. Well, here it says color. I'll say color slash intensity. Color slash intensity. And these co-occurrences are not arbitrary, but what makes a texture is that intensities or colors repeat themselves in a textured region in certain distances and certain angles. Think about a checkerboard. Let me come up with something like this. This is a tiny patch taken from some image, and we would be able to refer to it as a checkerboard. Right? There is a certain frequency, so black, 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 white, 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 black, 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 white, white, white. This black pixels. If there is one black pixel, there is a high chance that there is another black pixel immediately to the right of it, as well as, say, there is a high chance that there is another black pixels 5 pixels to the right of it. I know, I made this number up here, so this is black, 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 so 4 white pixels 4 black pixels in a row followed by 4 white pixels. So then therefore there's like, you know, either there's another black pixel immediately to the right, or with a certain delta there will be another black pixel. That is to say that black pixels co-occur at a certain spatial distance and at a certain spatial angle. For instance, not only along the x-axis but also along the y-axis, and what is characteristic for these checkerboard things is also with an angle of 45 degrees. That is the assumption here, that a texture is something where intensity or color values repeat with certain spatial frequencies and certain angular displacements. And that is to say, so these co-occurrences are understood with respect to distance and orientation. Distance and orientation. And let me see if the black one runs better, because this one is losing it. Doesn't make a difference. So okay, I'll press harder. If we accept this as a reasonable idea for how to characterize what is going on texture-wise in a local neighborhood surrounding a pixel in an image, well then how would we compute such a matrix G? Let's look at it. So we have this matrix G, and I will be referring to it, to its entries using the indices mu and nu. Two beautiful Greek letters. And if we compute the entries G mu and nu for, you know, mu and nu depends on the size of the local neighborhood we are looking at. Not only do the values of that matrix depend on the size of this, no, these actually depend on the number of intensity levels we have, but not only do the entries of this gray value co-occurrence matrix depend on the overall number of different intensities or colors we have, but given what I just said, they will also depend on a parameter for distance, d, and an angular parameter, alpha. And therefore, with all of this, we would say that the entry g, mu nu, of a gray value co-occurrence matrix for parameter d and alpha is given as the number of pairs of pixels in okay, so for the number of pairs of pixels, and these pixels are called Fij. This one has an intensity value of mu, and Fkl, and this one has an intensity value of nu. Number of pairs of pixels in the n by n neighborhood. Okay, so what does that mean? This is still not clear. We have a very large image. I don't know, make a larger image around here. Then there is some pixel x and y. And for this pixel x and y, we are now going to compute a gray value co-occurrence matrix G. And in this gray value co-occurrence matrix, we count number of pixels. I don't know, say here is one, and let's call this one Fij, and here is another one, let's call this one Fkl, and they are at a distance d. This is actually a stupid example, boring one. Let me choose another one, like I don't know, here. Let's go for this one. Fkl. these two pixels are at a certain distance d, and they are at a certain angle alpha. Right? We fixed that d and we fixed that alpha before we set out to compute such a matrix. For instance, d could be distance of 2 pixels and alpha could be 0 degree. So we just look at how often does a black pixel reoccur if there is another black pixel 2 pixels to the left, for instance. Right? But of course this will also happen for white pixels. So we just count how often do 2 pixels of the same color or of a color mu and nu occur at a certain distance and at a certain angle within a certain neighborhood. Damn it. Okay, it's actually it's really like easier to grasp than to talk about it, but this is what we do here. Right. It can of course happen that we are given I don't know, one pixel is white and the other one is black. So then we would count a co-occurrence between white and black at a certain distance and at a certain angle. Right. And in this image, there's just 2 colors in this neighborhood. But of course, if we're talking about intensity images, there can be 256 different intensities, and so these will be typically, if we are generous, matrices of size 256 by 256. And each entry in this matrix will call a count. How often does intensity mu co-occur with intensity nu? Yeah, and what makes it, I don't know, why would we say, I don't know, say distance is 2 pixels and angle is 45 degrees? It's very arbitrary, right? So computing just one such matrix may not be enough to actually capture what is going on. And therefore, let me write this down here. Important, usually several choices, of pairs of d and alpha have to be considered. That is to say that if this is going to be used in practice, then yeah, well, for every pixel in the image, we have to compute several of these matrices. It's of course, in a sense, a memory disaster. This is not so much a runtime disaster. If you think of it, this can be done very efficiently. Right? In the most naive way we can think of it, 4 nested for loops. One for loop over all the pixels in the image, and then but the outer 2 for loops over all the row and column coordinates, then 2 inner for loops over the pixels in the local neighborhood. In languages, compiled languages such as C, this doesn't matter. It's really, really efficient. So it's not, this can be computed, it's just counting. There's no real, elaborate computation, but just counting. Can be done efficiently, but it does require a lot of memory if we were to do this in this way. So what do people do? Quite typically, they do not compute this for every pixel, but sort of subsample the image, just do it for every second pixel, and assume that every pixel in between has the same co-occurrence. This is, very pragmatic, But there is still another issue now. We have computed several co-occurrence matrices with different choices of D and alpha, and typically that's something really like 2 pixels or 4 pixels for distance, and alpha is 0 degree, 45 degree, 90 degree. Why? Because, you know, because of course you can go for alpha is 38.7 degrees, but nobody does this. But still the problem is, what do we do with these matrices now? It appears to be a good intuition to think of texture as being something we can represent in terms of counts of co-occurrences. Right? If you think of it, the entries of this matrix will have a totally different value for a very homogeneous region. Every pixel is black in this region. All the co-occurrences we count are basically between black pixels. If it's a checkerboard region, we will count co-occurrences between black pixels, but also from black to white, and co-occurrences between white pixels. If the region is striped vertically, we will count co-occurrences between black and white, and white along a direction of 0 degrees. But if we were to count these occurrences along a direction of 90 degrees, we would only count black to black and white to white. If we were to flip the striped patterns, the situation would be flipped. So these co-occurrence counts really, you know, are able to identify certain structural properties of a textured region in an image. And now we have these humongous matrices and want to use them to, I don't know, evaluate the similarity of 2 pixels. Because in the end, we want to segment the image into region and not just to characterize texture at every pixel. We want to use this characterization for sort of another subsequent processing step. Do you see a problem with that? How do we compare to matrices? How do we, you know, in this predicate idea, now we have computed these co-occurrence, like say 6 different co-occurrence matrices for every pixel. And we want to use that to check if 2 neighboring pixels fulfill the same predicate, because we want to somewhat segment them into a coherent region. Just to evaluate these predicates based on these matrices would again require us more for loops over, I don't know, objects, matrices of size 256 by 256, right? If we do not subsample the number of intensities in the image. Does that sound like something very efficient? No, it does not. It does not, right? So the question is, given these simple counts, can we derive something like second order features to characterize these count statistics? Can we further compress these counts into fewer numbers? And if I ask that question the way I did, then it appears somewhat self-explicatory to expect that the answer is yes. And so here's just a couple of examples of measures derived from G. Once more, of course, we could work with these gray value co-occurrence counts immediately, but it's a bit cumbersome. So is there some way for us to compress the information contained in each of these matrices into maybe just a single number? Let's see. There are many possibilities, and many possibilities have been studied. But I will just show you a couple of them. There is one characteristic that is called energy. And this is given as E for D and alpha, just as the sum, where mu and nu range over all the intensity levels we are given, and we just compute the square of G mu and nu of D and alpha, so this is squared, and divided by the total sum. Mu nu, G mu nu, D and alpha. This, I mean, it's, you know, these are definitions. These are definitions. What does this measure? What would the energy measure here? Why is it possibly called energy? So first of all, this normalization constant adds up all the counts we have in our matrix, right? Say certain co-occurrences appear more frequently. Say black to black is more likely than black to white for whatever reason of texture we're given. Then the transition from black to black will have a higher value than the counts of transitions from black to white. And we even make them larger still by squaring that. And then we divide it by the total number of occurrences. So this measure called energy would actually be of high value if we are dealing with a region in which certain transitions occur way more frequently than others. In a region that is very noisy, like if you just create a noisy image and cut out a small patch, compute the gray value Cooccurrence matrix, then it is equally likely to observe a transition from black to black than from black to some gray or from black to white. So all the occurrences, co-occurrences are more or less equally likely of equal counts, then the energy would have a very low value. But if there is a certain co-occurrence or several co-occurrences that are way more frequent than others, then the energy would be higher. So this is, in a sense, a measure of inhomogeneity. If the energy is of homogeneity, if this energy is very high, then it's more likely that the region from which the co-occurrence matrix was computed consists of, well, homogeneous subregions. Another measure is called contrast. Contrast, and let's call it C of D and alpha. This is just, I should have started with this one. The sum mu nu, all the intensity values. We just sum everything here. Mu alpha. Yeah, I guess there's not much to say about this. So therefore, let's move on to the last one we'll look into today. Homogeneity. H, let's call it H of D and alpha. This is given as the sum where we sum over all intensities, mu and nu. Then we have G, mu and nu, D and alpha. And all of this is weighted by 1 over 1 plus the absolute norm or difference between mu and nu. You can write this in a different form, then it becomes a bit clearer why it's called homogeneity. Can, for instance, express this as the sum where an index L, ranges from 0 to L minus 1. And then we have 1 over 1 plus L. And here we then have another sum where the norm of mu minus mu equals L, G of mu d alpha. So this actually, yeah, is just a weighted contrast where the weight is given by the difference of the intensities that co-occurred. Why would I talk about all of this? Why would I talk about all of this? Never read about it anymore. Seems to be a bit dated. But these kind of things do have their value. They are actually really used in practice. Right? There is this difference between stuff people think about in their research labs and write scientific papers about and publish them, and everybody else then uses these things. And so that is on the one hand side, people do in the lab and publish scientifically. On the other hand, there is the stuff that works reliably in practice. Right? For practitioners, it is not necessarily the most important thing to have the latest technology, stuff that some people in some experiments found to work well on some data, but practitioners prefer to use stuff that has stood the test of time, that not just has worked in the last year, but has worked over decades and successfully so. Right? This is something these texture features clearly have on their side. They are well established, their properties are extremely well understood, and it is known that they work well, whereas the latest things, I don't know, in our case, latest things such as SIFT, SIFT by now is also well established, but the latest stuff is not necessarily generally applicable. We just don't know that yet. It takes time to test latest ideas on different scenarios and maybe actually realize, it works here, but it doesn't work there. Right? So these things are used quite frequently out there in the real world. Actually, I have used them recently, or a PhD student of mine has used them recently in a research project where we tried to identify plant diseases from taking cell phone pictures of leaves of plants, and there were like some leaf spots there caused by some fungal infection of the plant. The question is, looking from these diseased regions on the leaves of the plant, can we actually say what disease it is that is currently infecting the plant? Because if we can say that, we can sort of, use the corresponding herbicides to get rid of the disease. And the idea was to do it on cell phone cameras, right? Or on cell phones, using cell phone camera images. Cell phones are great, but compared to your, desktop architectures or laptop architectures, or server architectures for that matter, the computational possibilities of a cell phone are still very much restricted. It's like they have powerful processors these days, but their power pales in comparison to other computers. And typically computer vision is done on really powerful computers, because by now you have realized that it involves rather intricate computations. So for this project with the cell phone cameras, the question was, we need something that works, for which we know that it works, and it should not pose or should not overburden the capabilities of the processor and memory of the cell phone. And this is where these things shine. This is where these things shine. They work really well in practice, and compared to these latest things such as SIFT or Hawk, they can be computed rather efficiently and do not overburden limited processing environments. Okay, now we are done with this. This is all. We now have talked about predicates, which I said are synonymous with features. Of course, to wrap this all up, I now need to talk about how to use these predicates in actually segmenting an image, right? Ever so briefly talk about segmentation algorithms. And let me see if the red one writes slightly better. No, it is not. So once somebody has agreed on how to define a predicate which we use to identify homogeneous regions, the question is, how can we actually do it then? Once we have these predicates, how do we turn an image into a collection of regions? There's two basic major things we can do. We can think about merging, and we can think about splitting. How do I do it? Let me do it one by one. When we resort to the idea of region merging, resort to the idea of segmenting images by merging smaller local regions into larger ones, what we do is the following. We initialize a number of seed points. And grow regions Ri by means of adding adjacent pixels until, here is a repeat until loop, the evaluation of whatever predicate we have chosen, Ri, does not hold anymore. So this red one has disqualified itself. I will not use it any further. That is, we are given an image, I don't know, randomly select a couple of points, some number, we call them seed points. We evaluate their predicate, or the predicate there. And then we do this for all the adjacent pixels of the seed point. And if one of the adjacent pixels of the seed point fulfills this predicate, we combine it with the seed point to form a larger region, now of 2 pixels, and then maybe 3 pixels, and then 4, and so on. Then we do this for all the neighboring pixels of the recently added pixels to the region. And if there are neighbors of those pixels which also evaluate to the same, have the same feature, fulfill the same predicate, we grow that region further. Of course, we can think of it that can grow a region sort of pixel by pixel until there is no neighboring pixel anymore that would meet that predicate. Right, that is what this does. This is a good idea. It has a couple of problems. First one, how to determine the number, among others, and the seed points. Number of seed points. Right. If we are very unlucky, we would choose 3 seed points which within one region. And then we would sort of grow these regions. So the three initial seed points we would have chosen would all fall within something that we as human observers would call a region. And so we would have chosen three seed points from a region, and then grow the region. And what about other parts of the image? If there is no seed point, we cannot identify regions there. So it's a bad thing. Then also, the way in which we merge neighboring pixels into a region might actually be critical. So the merge sequence might be critical. Here's another hypothetical situation that could happen. So we have already grown two regions, and they have grown very close to each other, and then there is a pixel in between these two regions. And as it's a pixel in between two regions, it may actually sort of be close to the pixels in the one region or to the pixels in the other region, not in terms of its spatial distance, that is for sure, but maybe also with respect to its predicate. To which of the two regions do we assign that pixel? Right? And if we are unlucky, it may happen that, I don't know, by means of these growth processes, certain bridges between regions could occur, merge very fine filaments of strings of pixels. It can look crazy. It can look crazy. And therefore, this may actually lead to over-segmentation. Segmentation. That's not so nice. What to do about this? Already said there is yet another paradigm. Let's look into that one. It's called splitting. Here, what happens is that we iteratively divide the image, and that is to say regions, into subregions. This is great. We don't have to worry about seed points. We sort of begin by looking at the image at large and say divide it into two most homogeneous subregions, and then each of the subregions will be again divided into two or more subregions. And we continue this process until all regions fulfill this predicate. That is to say, we can actually summarize this. Really this is horrible what you can see. Try the green one. In other words, this is something like while not P of Ri equals true for all I. Here's a while loop. We select a region Ri where P of Ri is false. So say we start with the overall image, which we understand as just one region. And for that region, it is rather intuitive that the predicate will have different values for different pixels in that image. So we would have identified the image as the region that needs segmentation. We therefore divide Ri into subregions, RIL, and replace this region, which is just a set of pixels, by a set of sets of pixels. RI1 all the way up to I don't know, L. Right. So yeah, sounds very intuitive, but of course, if I identified problems for this merging approach, then here the obvious problem is how to do this divide. Like, I mean, so we are given the overall image, and we know that it consists of several subregions, and then it says divide it into subregions, and then for each of the resulting sub, continue this. Like, how does this division take place? How to divide Ri? Right? Nobody can really tell you, and so therefore there is a final approach, and then we are done with this. The idea is now to take the best of both worlds, to come up with a region segmentation algorithm that integrates good ideas from this idea of merging and good ideas from this idea of splitting. And that is called split and merge. So, split and merge. And this is actually what I guess is done in most of the libraries, OpenCV or processing software such as Photoshop or GIMP. There are functionalities to divide images into regions, and I guess they all resort to that. That is to say that we alternatingly apply split and merge operations to an initial segmentation. So what that is to say that we do not choose split seed points, and we do not consider the overall image as just one region at the beginning, but we assume that there is an initial segmentation. Now the question is, well, how do we assume that? What? How would that be done? And the cool and simple idea is, for instance, using quad trees. That is a great opportunity for us to study yet another data structure that comes in quite handy when we do image processing and analysis. I don't know, let me come up with a stupid image, whatever, make it this one. So here is an image consisting of 3 regions. One is a circular region in the upper left, then there's this square and the background. And when we begin this split and merge algorithm using quad trees, we would say, well, this image consists of 4 regions. That is what we do. And that is to say, we compute compute an initial, in parentheses tiled segmentation. This is what I already did. I tiled that image into 4 regions. And while this predicate is not true for all VI's, we merge quadruples of regions. We merge quadruples of regions. I just realized that I have to introduce more regions there to keep up with my algorithm here. So this is sort of the first division into 4 tiles, and of course this would become a quad tree once we begin dividing every tile into further tiles of 4. And let me do this here and here and here and here and here and here and here. So this is now a beautiful quad tree. And what this algorithm does, it starts with some quad tree like that, and then begins to merge neighboring tiles. For instance, it would merge all of this into one region, and all of this into another region. And then we would realize that it is a stupid idea to merge this into one region. You can see that, right? It's a stupid idea. Now it's not homogeneous anymore. And therefore split resulting regions if necessary. Split resulting regions if necessary, which is to say, in this contrived example, we may therefore end up with something like, let me make it fat, like so. From merging these 4, we would get a larger tile, but that tile would not be homogeneous anymore, so we'd sort of cut out this tile again. And we would remove sort of like this, if there's just 1 pixel or whatever, then there's a minimum for the resolution that does not go down to the pixel level, but I don't know, like 2 by 2 squares in the image, and remove small regions so that we don't have to worry about them in later iterations. Regions. So that is it. It combines tiles into larger regions, checks if everything is okay. If not, it throws out those tiles which violate the predicate of homogeneity. And if the regions that are sort of thrown out become too small, they are not considered any further, because then it becomes too burdensome. So this is, we begin with a certain segmentation in terms of regular tiles, combine them into larger ones, identify parts that should not belong to this larger region, get rid of this. In the next iteration, we would, for instance, at some point we would find that there is some homogeneous region here, maybe, I don't know, it's actually like this, whatever, but if it becomes too small, nobody cares. And yeah, I hand wave it away because time is running out, and I wanted to tell you about segmentation. Of course, all of this was a bit rushed, but I already told you last time that I had to restructure our lecture this semester because I have to talk about neural networks later on. So therefore, you now at least have a certain idea as to how we can segment images into regions. Next time we will study another crucial question, namely the following. If we are given an image, I don't know, And we have already segmented it into regions. I don't know. So let's say this is actually already the result of the segmentation. This is now a different picture than the ones I have shown you so far. So far our question was, how can we determine that there are different regions in this image? Let's say we have already run this algorithm. Now the question is, how many different regions are there in the image? Well, that is very easy for us to answer. It is 2 or whatever, 2 regions, subregions in the image that are topologically disconnected. But how is the computer to know that? How would the computer know that, like, the predicates for these pixels are all the same, right? Because there's, say, 2 black squares on a white background. So predicate-wise, these pixels are the same as these. And how would the computer know that they are actually not, in the sense that those pixels belong to one region and these pixels to another? We will study how that can be decided. This is again something that is very well understood. It is a fun occasion for us to acquaint ourselves with highly efficient algorithms for certain image processing problems, so-called 2-pass algorithms. We'll use that to decide how many regions are there. We'll look into something that is called the chamfer distance from a pixel to the boundary of the region it belongs to. And we will finally study the question of, now we know about regions, but what about lines? How can we identify coherent line structures in an image, which is a great idea because at least the human-made world consists of lots of things that are characterized by rather distinct edges. How can we identify an edge starts here and ends here and whatever goes from that pixel to that pixel? It will lead us to the question of the half transform. Once we have done that, we will then study neural networks ever so briefly. That's all I have for today. Do you have any questions? And next time we'll open the door because there's way too hot in here. Great, see you on Thursday.